Thank you so much for introduction, Jose. Good morning, everyone. Thank you so much for being here today. So today I'll be addressing a duality between two families of particle detector models. Here's what I planned today. So the talk is based in this paper that I published this year with Thales. The outline will be as follows. First, we're gonna give a quick overview about a topic that maybe you are not familiar with, or maybe you are having some dreams with, particle detector models. Then we are gonna consider instance where we have the particles coupling to the amplitude of a quantum field, instance where we have the particle coupling with the derivative of the field, and then we are gonna see how we can get a duality between those two models. Finally, some comments on how this duality translates for cases where we can study entanglement harvesting, and the concluding remarks after that. So, particle detectors, what they are. Essentially, we are talking about models where we have a finite dimensional quantum system that is interacting with a quantum field. Here we have infinitely many degrees of freedom, complicated, but here we are at home, we are safe, we know how to deal with those systems. So we couple them, we can apply local operations here, like measurements for instance, and hopefully we can learn something interesting about the field. For instance, using such kind of models, we can implement quantum information protocols and quantum field theories. We can quantify entanglement present in quantum fields. We can even establish outstanding results like entanglement harvesting, where you have two particles that, even though they are space-like separated, they can become entangled because they are interacting with the field. There's also the phenomena of quantum energy teleportation. It has been known for a while that we can teleport states of quantum systems, but now using such kind of models, it can also be shown that we can teleport energy over long distance in a time which is way shorter than the time that, let's say, the typical dispersion of energy to travel from a place to another. And last but not least, such kind of models can also be used to probe the geometry and the topology of the spacetime. So the simplest model is the so-called Unruh-DeWitt model, where we have simply a scalar quantum field coupled to a qubit. But don't be foolish by its simplicity. Despite its simplicity, it's a very I would say it's the solid block where we build our intuition about mostly of particle detector models, and it essentially captures all the essential features of how an atom can interact with the light in the absence of angular momentum. So the setup for the model is as follows. We have a field in a n+1 dimensional space-time, and this is a scalar field. Here I'm asking that this field satisfies the Klein-Gordon equation that might be coupled to the curvature, the Ricci scalar of the space-time. So we have the field, and we have the qubit, which is simply a two-level quantum system, a quantum system that can have two possible energy levels. Here I'm employing the notation G for the ground state. Then we have the excited states, and those levels are separated by a fixed energy gap, omega. And how do we set up the interaction? How we can put this qubit to interact with the quantum field? So we have simply this type of interaction. Here I'm giving the expression of the Hamiltonian density that's going to define the interaction. So I couple the field with this operator here of the qubit. This is an operator that acts on the Hilbert space of the qubit. Here I'm defining the ladder operators, the operator that takes the excited and lowers to the ground, and the operator that takes the ground and raises up to the excited state. And in order to address more general models, it's usual in the literature to consider spacetimes metering function, which is to say physically that we are saying that our interaction is going to be localized on spacetime. And the essential, now talking about physics. So we have this model, we have the interaction, what we can learn from it. So the usual setup, we can start the field on both the field and the detectors are initialized on its respective ground states, meaning that the field is in the vacuum, there is nothing there, but you know that nothing can be complicated in quantum field theory. And the qubit starts on its ground state. Then we evolve it according to the interaction that I described on the previous slide. And after that, remember, we have the field infinitely many degrees of freedom. It's complicated. We don't like that mathematically. So we trace out, we ignore the degrees of freedom of the field. And then we got this object here, the reduced density matrix that can allow me to predict statistics on measurements that I might perform on the detector. In particular, there is this celebrated result where is the matrix? Oh, I believe there was some porting issue here to Windows for Mac, but trust me, there was supposed to be a matrix here. Probably you know this by heart. It's a good exercise. Try to imagine which matrix is here. So, but essentially, we have, to lean the order on the coupling constant, you can show that you have a matrix, essentially a 2 by 2 matrix, where the probability that the detector gets excited, you'll be given by the square of this number here. So we have this integral here, which relates the Whiteman function with the space-time metering of the detector. And then by squaring this term, you get the probability that the detector can be excited. So pay attention here, what we learn here. Even though the detector started in its ground state and there was nothing there, the field was in the vacuum, due to the vacuum fluctuations of the field, the detector can become excited. So that's the message here. Okay, so here we saw a simple model where we have a detector coupled to the amplitude of a field. Of course, in the literature, you can consider, people have been considered many other models with more complex quantum systems, more complex fields in the sense it can be a complex quantum field, it can be a spinor, a fermionic field. But one other model that I would like to call attention to is a model where we couple our detector to the derivative of the same field we considered before. And by derivative, you can imagine that I'm taking the derivative with respect to the proper time of the detector. Remember, the detector is in space-time, following a trajectory, so I can define derivatives with respect to its proper time, for instance. And this kind of model is particularly interesting because in literature, people use it to avoid some infrared divergence that can appear in 1+1 spacetimes, or even more, in the work of those gentlemen here, they have shown that if you have a derivative, a model, where you couple the detector with the derivative of the field, you can use this model in a lower dimensional spacetime to mimic a model where you have an amplitude coupling in a higher dimensional spacetime. Okay? So, mathematically speaking, what we have now, mathematically speaking, what I'm saying by changing the model is exactly this. Instead of coupling the qubit with the amplitude of the field, we are going to couple it to the derivative of the field, right? Here we need to be careful just to redefine what we mean by redefine our quantities. Here I'm going to take both coupling constants are going to remain the same. But here, since we are changing the units here, we are going to redefine things in a sense that now this mirroring function in this new model is going to have one last dimension of energy. And also here, again, since we are not sure just to keep the generality here, we are going to also allow that in this new model, the qubit might have an energy gap, which is time dependent. All right? So now I ask you the main question of this work. When we change, we start with a model where we couple the detector to the amplitude of the field. And now we move for a model where we couple to the derivative of the field. What's the change in physics? Mathematically, the change in physics will be represented by how this term here changed. Because remember, if we take the square of this term, it's going to give us the probability that our detectors are going to become excited due to the interaction with the field. The idea here is that we can employ some mathematical trick in the sense that notes that we can pull out time derivatives here, and essentially, to make a long story short, you can apply integration by parts here as to try to relate this term here with the original term we had before. So now I'm going to impose that the physics is the same. I'm going to say, okay, I wanted the same physics on those two models. So what's the condition that my detector, described by this mirroring, needs to satisfy? Okay, mathematically we have this condition. It's a nice looking equation, but it doesn't tell us that much. We need to learn something else. So as good physicists, what we should do? We should make additional assumptions. So I'm going to make 3 assumptions in order to simplify this expression. I'm going to assume that the space-time volume around the trajectory of the detector is constant. I'm going to assume that this mirroring can be split into 2 terms, a switching function, a function that controls, that turns on and off my interaction, and a shape function that describes the shape of my detector in its rest frame. I'm going to also assume that both detectors have, for both models, they have the same shape and the same couplings. So under those assumptions, we are able to relate the switchings between those 2 models. So don't lose track. 3 minutes? Oh, time is relative. So don't lose track here. Here we have imposed that the physics is the same on those 2 models, and then we got this relation between the switchings, right? Now I ask you, can we go further? Yes, we can make yet another assumption, and we can obtain a very nice relation that essentially is the core of our work. So if you consider the limit where the energy gap is infinite, is very large, it can be shown that the 2 models, the linear coupling one and the derivative coupling, are going to yield the same physics provided we essentially rescale this. So what's the lesson here? If I start with a model, an amplitude coupling model with this switching, and then you have a model with derivative coupling, but you use this switching, then they are going to have the same results. And then you say, cool, but you are assuming that omega needs to be infinite, right? So this mathematically is okay, but physically doesn't make that much sense. So the question we should ask ourselves now is that, okay, is there any value, any feasible value of omega that can make this duality to approximately hold? It turns out that yes. For our friend here, this friend that appeared maybe 3 or 2 times today, for a Gaussian switching, which is very physical, it's usually in literature, it can be shown that if you pick values of the energy gap that are as physical as 5 times the time scale of the interaction, you have the chi tilde, the general switching for the other model is going to respect the rescaling. And if we have the rescaling behavior, we can be sure that the linear coupling model and the derivative coupling model yield the same physics, right? Just to finish, just a quick comment here. If you work with non-smooth switchings, like this one here, you need to pay a high price. You see some inflation here that you need to pay on the energy gap. And before finishing, I would just like to quick mention that this result that we just presented, it also carries out perfectly for the case we have two detectors, meaning that it has also an impact on entanglement harvesting, right? I don't have that much time here. I'm going to leave just as a material that you can check maybe on the paper. So here, believe me, this result is also valid when we are in the context of entanglement harvesting, okay? Maybe I'm a little bit over time. Okay. I'm going to stop here, maybe to take one or two questions. Thank you so much for your attention.